come and visit us, or that was the original idea, but unfortunately, obviously that's been cancelled. So we're very grateful that she can give this Zoom seminar to us. Rachel is an instructor of medicine and an associate epidemiologist at the Channing Division of Network Medicine at Harvard Medical School and Brigham Women's Hospital. She works in the field of metabolomic epidemiology, particularly on common complex diseases, particularly respiratory diseases and neurodevelopmental disorders. And she's also interested in combining or novel ways of combining metabolomics data with other omics data. And today she's going to talk about the COMETS Consortium and the challenges of meta-analysing metabolomics data.
Thanks very much, Isabel. Okay, I'll just share my screen now. So firstly, just thank you very much for having me remotely. I was obviously very disappointed that I wasn't able to be there in person, but it's wonderful to speak to you all this way anyway, and a great honor to be invited to take part in this great seminar series. So just because I can't meet you in person, a little background about myself. I'm originally from the UK, despite the fact that apparently my accent is starting to wane slightly. Did my undergrad in biology at Warwick before doing a master's and MPH at Nottingham. I had a few years at the Institute of Cancer Research before I moved to Imperial to do a PhD in the molecular biomarkers of non-Hodgkin's lymphoma. This led to my first postdoc at the Harvard T.H. Chan School of Public Health in the lovely city of Boston. There I focused more on the metabolism of prostate cancer. Then I moved over to the Channing Division of Network Medicine, where I am now, where, as Isabel mentioned, my focus switched more to kind of respiratory disorders and integrative omics. But I still tried to come home as much as possible, which is why I was very excited to come home, but never mind, I'm sure I'll be there in the not too distant future. So just to give you a brief overview of what we do at the Channing Division of Network Medicine. So this is part of Brigham and Women's and Harvard Medical School. And the overall mission is really to use kind of systems, methods, and network approaches to better understand complex common diseases. It's split into 3 units, the chronic disease epidemiology, systems pathobiology, and systems genetics and genomics, which is the section that I work in. And what we do in this section is really considering all the kind of omics that you can think of and different ways of analysing these data and integrating them. Again, primarily with a focus on respiratory disorders, but kind of moving into other phenotypes more and more. And then obviously, again, as Isabel mentioned, my primary interest is really in metabolomics. So apologies, I'm sure this will be repetition for some of you, but just to give you a brief overview of where I see metabolomics and in particular how I kind of see it fitting into the study of health and disease. I'm just going to give you a very brief overview. So if we think of this very kind of simplified version of the central biological dogma, the metabolome is really this kind of intermediate between genome and phenotype. And for this reason, it really provides us with kind of a downstream measure of gene environment interactions and kind of the preceding omes that really lead to the status of the current phenotype. And when I say the metabolome, what I'm really talking about is the components of these kind of metabolic networks and kind of all the chemical reactions, the pathways, and the regulatory interactions that really determine the status of a biological system. So metabolomics, therefore, is just the global profiling of these small molecules or metabolites, by which we really mean anything less than 900 kilodaltons, to study these to try and understand what is happening in a system. And the metabolome includes not just endogenous metabolites, but also a variety of exogenous metabolites, things such as food additives, toxins, environmental chemicals. And one of the great strengths of metabolomics, it can be measured in almost any biosample you can think of, from blood to bone, urine, bronchoscopy, saliva, all different kinds of samples, which really gives you that huge advantage that you can measure the biosample that is really of most relevant to the phenotype or the disease that you're interested in. And there are 2 different ways that metabolomics can be performed, either by nuclear magnetic resonance spectroscopy or mass spectrometry. I won't get into these details, I don't really think it's a particular interest to the talk, but just to recognize that there are these kind of 2 different approaches which are ultimately doing the same thing, but really provide you with slightly different but complementary information. And similarly, you can either, metabolomic profiling can either be performed in an untargeted way, which is just the kind of comprehensive global analysis of all the metabolites in a system. And when I say all, I say this with a caveat that really no method is currently able to measure all metabolites, or even close, really. But it's kind of the best that we can do right now, is measuring as many as we can. But because of this approach, what you're getting there is relative abundance rather than absolute quantification. In contrast, if you wanted to do targeted analysis, this is where you kind of define from the outset which metabolites you want to measure. You measure a much smaller number, but you are able to get absolute quantification, kind of absolute levels of those metabolites, which in some instances, you know, for example, maybe the development of biomarkers could be more useful than the kind of untargeted approach, which is better suited to discovery-based analyses. So thinking back to this idea of the central biological dogma, the way that I see what the metabolome can tell us is really it provides this kind of instantaneous snapshot of the physiological status of a biological system. And because of this, it's able to tell us about the past. So as I mentioned, it's kind of the metabolome is really this downstream product of an individual's previous environmental exposures, but also their genetics and the interactions between them. It can tell us about the present, what is an individual experiencing currently, again, both thinking of environment and phenotype. And finally, and what is of interest, or of most interest to a large number of researchers working in this field, is that it can also tell us about early stage pathogenesis, or give us clues about what is going to happen. So again, this is particularly of interest for people who are looking at developing biomarkers. Because if we think of this kind of causal pathway from a healthy biological system to a diseased one, or even from kind of a baseline state to some phenotype of interest, we can really identify metabolic biomarkers all the way along this causal pathway. So including biomarkers of susceptibility, prediction, diagnosis, endotyping, prognosis, therapeutic response, or recurrence, as well as exposures all along this pathway. And again, you know, what's so powerful about the metabolome is that these biomarkers are not just clinically useful, they also provide, by considering, you know, what the biomarkers are, what pathways they're involved in, it really provides us with this kind of improved understanding of the biological mechanisms underlying this causal pathway. And I think that the utility of metabolomics is really exemplified by this figure here, which just shows the number of research publications with metabolomics, or some kind of iteration of metabolomics in the title, that have been published since the year 2000. You can really see there's been an exponential growth in these kind of studies, with 2020 already on course to overtake 2019. So really, you know, a rapidly growing field that more and more people are becoming interested in. But there are some issues with metabolomics. You know, one of the greatest strengths of metabolomics, as I mentioned, is this kind of sensitivity to environment and phenotype that allows us to use this information to understand those factors. However, this can also lead to kind of noise in your data. So heterogeneity in metabolomic findings can stem both from biological heterogeneity, things such as gender, smoking status, age, you know, health status is not related to your phenotype of interest at the time, and particularly diet, which is a huge area of research in metabolomics, the impact of the diet on your metabolome. In addition to this, there's also technological heterogeneity. You know, a lot of this is common to kind of any omics, but some of it is much more specific to metabolomic data. You know, so things such as the fasting status of a subject when you collected their sample, how that sample was collected, how it was then stored, and how long it was stored for. All these things can also influence the metabolic profile, and really must be therefore considered when performing your analyses. And furthermore, you know, it is still a growing field, and a large number of the metabolomic cohorts, with a few obviously very notable examples, including some of the cohorts you have there in Cambridge, have limited sample sizes to deal with this kind of noise and heterogeneity. So as with you know, most other omics, you know, particularly something like genetics, one of the best ways to deal with this would be to perform meta-analyses across a large number of studies to look at your phenotype or disease. to provide yourself with more power, the ability to make more precise effect estimates, and also importantly, the ability to make these more generalizable across different types of populations. However, apologies, it's early in Boston, so meta-analyzing data is not necessarily quite as simple as you might think. So if you think of metabolomic data, one of the first things, as I mentioned previously, is that you're really not measuring the whole complement of the metabolome. In every instance, you're just measuring a subset. And there are also a number of different ways that you can do metabolomics. So either it's often done in-house by the laboratory in your institute, or it's done by another academic partner. There's also a number of commercial entities that will also perform metabolomic profiling for you. The issue is that each of those, dependent on the particular technology that they use and dependent on the population being sampled in that particular analysis, you're always going to get not just an incomplete coverage of metabolome, but a slightly different subset of the metabolome. So, study A might have 1,000 metabolites, study B might have 800, but only 600 of those are in common between those two studies. So you're not always measuring complete like with like. The other very important point is that there's inconsistent nomenclature between these different studies, between these different platforms. So the way that you get your metabolite data reported from lab A might not be named, it might be the same metabolites, but they might not be named in the exact same way that they are named in study B. And part of this is just because there's a number of different kind of underlying bases that people use to name their metabolites, such as HNDB or KEG. But really to date, there isn't an accepted gold standard in the community about which one of these should be used. So namings can vary lab by lab. And also just, if you look at this here, so this is just many of the different names for tryptophan with at least 71 other synonyms. So again, you need to be able to, aligning these different databases when the names are not necessarily the same and they don't have the same IDs can be complex. And then finally, and this only applies to untargeted data, but as I mentioned, rather than absolute quantification, when you get a metabolite data set, what you're getting is the intensity of a given metabolite relative to the other metabolites in that data set. So again, it's not entirely comparable between different studies. So all of these things kind of add up to make, has so far hampered large-scale meta-analyses of metabolomic data. So this is where consortia come in. And so today I want to talk a little bit about the Consortium of Metabolomics Studies, or COMETS, again, which some of you may already be aware of. Some of you may not. So the Consortium of Metabolomics Studies is this extramural intramural partnership among prospective metabolic epidemiology studies. That is epidemiological studies, most commonly cohorts, who have biological samples on which they performed metabolomic data. It was actually initiated originally and is funded by the National Cancer Institute in the US, although it is global and it really doesn't have, at this point, any strong focus on cancer. It's just a lot of the initial cohorts did happen to be cohorts looking at cancer outcomes. So the overall mission of COMETS is to really provide this framework to foster collaborations, novel projects, and specifically meta-analyses between existing metabolic epidemiology studies from across the world. And the criteria to join is you just have to be a prospective cohort with at least 100 participants with blood metabolomics, either serum or plasma, can be conducted in either MS or NMR. And you just have to have some kind of long-term follow-up for phenotype or disease. To date, I know the numbers are constantly going up, but I think we have about 60 studies, again, including some of the large ones that I'm sure many of you have worked on, including Twins UK, EPIC, the European EPIC, and many other studies from all over the world. And one of the first things that, when it formed, I think about 10 years ago now, one of the first things that COMETS really wanted to do was to facilitate these meta-analyses. And as I mentioned, due to the problems that I mentioned, conducting meta-analyses and metabolomic data is not simple. So what they did, led by the wonderful team of Steve, Ella, and Evie, was developed COMETS Analytics. So what COMETS Analytics is basically a functionality to allow us to conduct these meta-analyses without anyone having to share their data or upload their data, which bypasses a lot of these, especially the newer European rules about data sharing. So what it is it's an online cloud-based platform whereby anyone can register. When you go on there, you essentially input your data into COMETS Analytics. It will run your analyses, and then the PI of the meta-analyses will get the overall meta-analysis result. You'll get back your own results, which you're free to do whatever you would like with, but it means that at no point does the PI of the meta-analysis have to see your individual level data, and you don't have to even share code. It's all done through this system. And one of the best things about it is, because as I mentioned, aligning metabolites between different studies is a huge issue. So COMETS Analytics has this built-in metabolite harmonization feature, which is being continually updated, and which allows us to match metabolites between these different studies. So this is just a brief outline of the analysis pipeline. So as I mentioned, firstly, you map the metabolites across these different cohorts and platforms. Each individual cohort will prepare a file based on a common input file that we provide to them, and just essentially copy and paste their data into this data preparation file, including information on the metabolites, including covariates of interest, including these pre-specified models. So again, there's no coding or anything needed on the part of the cohorts. As part of COMETS Analytics, there is a data integrity check. So basically, we just check these files to make sure, and it's just an automated process, but we check these files to make sure there's no problems in the data, that the analysis can go ahead. It conducts these cohort-specific analyses. And again, the results of these cohort-specific analyses go back to the individual cohorts. And then finally, it conducts a meta-analysis, which is just a centralized analysis of all the different cohorts that have gone in. So as the PI, for example, for this project, I will just get these meta-analysis files to then move forward with the next stage of analysis. And just to talk a bit more about metabolite harmonization, the way this works is essentially when we, the curated input file that I mentioned has a number of different columns, and it's just essentially asking the PI of each individual cohort to provide as much information as they possibly have about the metabolites in their study. So they may have 1, 2, 3, 5 of these levels of information, and we can use this to match each new study back to this kind of master list. And obviously there's an order of hierarchy, for example, KEG ID is more useful than sub-pathway, but if we get down and sub-pathway is all the information we have, then we will use some kind of level of manual curation to try and identify, match it with something in the existing database. So this has been a huge effort on behalf of the data harmonization team to just work at developing this hierarchy and merging every new study into our master list of databases. But it's meant that we now have this huge resource where really we are able to directly compare metabolites from lab to lab. So to give you an example of really how this works in practice, I'm going to talk about the metabolome of BMI. So this is a project that I'm leading with Jess Kolaski-Sue, and together with an age meta-analysis, which is being led by Steve Moore. These are the first two kind of proof of principle studies to come out of COMETS. And really we chose BMI and age because these are the two of the variables that pretty much every cohort has, and two which we thought would really have a strong and measurable impact on the metabolome. So it would be good phenotypes to start with. So I'm sure I don't need to, again, say to this group, but as we all know, extremes of BMI can lead to serious health consequences in either direction, either too low or too high. And extremes of BMI is also a growing, a quickly growing public health problem all over the world. So again, a phenotype of interest to study. And because an individual's BMI really kind of manifests as due to these complex interactions between an individual's genetic susceptibility, but obviously, strongly interacting with their environmental exposures, it's kind of ideally suited to metabolomic profiling because, as I mentioned, the metabolome is really this downstream readout of the interactions between an individual's genetics and their environment. So very well suited to metabolomics. So with this in mind, our study had two main aims. Firstly, to just kind of look at individual metabolite BMI relationships between multiple cohorts using a meta-analysis approach. And then secondly, to evaluate the heterogeneity of associations by participant and study characteristics. So to determine whether our age BMI relationships were the same across, across genders, across different age groups, and across various other features, and then across the different studies that were included. So again, the methods were that we started by every individual cohort. We provided them with the input file, and then they ran their cohort-specific analyses through the COMETS analytics platform. We performed the meta-analysis. And then in order to kind of interrogate this data, firstly, we looked at a number of different methods for false discovery correction. We looked at heterogeneity, and then we looked at kind of biologically interpreting these findings through commonly used techniques in metabolomics, such as pathway analysis and metabolite visualization. So to give you an idea of what this input file looks like, so the first tab is the metabolites. So here they just, as I said, just provide all the information they have on the metabolites. The second is the subject metabolites. So here will just be a row for each metabolite, and then each column is all the samples, and you will have the actual intensity of that metabolite for that sample. The subject data is information on the subject, so covariates. And this is just the var map, which just maps the variable name to a description of the variable. And then finally, the one that I really want to show you here is this models tab. So as I said, these are the models that we predetermined before the analysis is run. So we use a number of different adjustments and stratifications to explore all the models that we think will be of interest to our results. And what is important to point out here is that, so for example, say a particular study didn't have information on, smoking group. In many cases, if you were just kind of sharing code with people, sometimes these models would fail and it would make it very difficult. What COMETS Analytics does is it's able to actually deal with missing data. So if there's any variable that a cohort doesn't have, those models just won't run for that particular so the models won't run for that particular cohort, but we will get every other model. So it just kind of keeps things smoothly running along and allows us to get as many models as we can, as many results as we can for each cohort. Additionally, we did look at stratification by geographical region. So you can see here that most of our cohorts were either from North America or Europe, but we did look to see if region made a difference, and we also looked stratified by platform. So we had we had data from 14 different academic and commercial labs among our results. So we also looked at stratification just to see if there was any kind of if the labs were introducing any heterogeneity into our results. So for the purposes of this talk, I'm mainly going to focus on our kind of model 1.1, which is our multivariable adjusted model, which was adjusted for age, gender, race, educational group, smoking status, alcohol consumption, fasting status, and nested case control status. And when I'm saying nested case control status, this refers to the fact that a large number of the cohorts were following up individuals for a specific phenotype. So we just want to take that phenotype into account. So if an individual went on to become a case in the specific cohort, then we just want to adjust for this in the model as well. So in total, we had 46 cohorts who agreed to take part in this study. This study was actually initiated quite a long time ago now, so the 46 does kind of represent the majority of the cohorts who were in COMETS at the time that it was initiated. Obviously, we do have a lot more now, so moving forward, meta-analyses have the potential to be even larger than this, but these 46 cohorts included a total of over 126,000 participants, and this just shows the breakdown here for each cohort by gender. And you can see that in total we had 56% of the subjects were female and 44% were male. And if we look here, this is just the mean BMI across all the cohorts, split down into geographical region. As I mentioned, you obviously noticed that Africa, unfortunately, at this point isn't really represented at all in COMETS. That is something we're working to remedy. We currently only have one cohort from South America and one cohort which is considered international just because it has multiple sites globally. You obviously notice here this kind of outlier. I will just point out that this study was particularly selected to be obese individuals, as was actually this Estonia study, which is just why this BMI is so much higher. And overall, the mean BMI of this population was 24.5.97. And you'll obviously notice here some kind of regional differences, whereby the mean BMI in Asia was much lower than that in either Europe or North America. And just a breakdown of some of the other kind of characteristics of interest in these studies, we had a variety of age groups, although the majority of our participants were white. The majority didn't have diabetes, which I'll come back to a little bit later on. A large majority were also fasted at the time of blood sample collection. Most were non-smokers, and most were not, did not go on to become cases in the individual cohorts of interest. So in total, we had 1,367 metabolites that we were able to harmonize across our studies. So because of this issue of the incomplete coverage of the metabolome, this doesn't mean that we were actually able to measure 1,367 in all of our cohorts. But in total, but we set the threshold of a metabolite must be measured in at least 6 cohorts to be included in our study. We considered a variety of different thresholds for metabolite inclusion, but this was the one that we kind of ultimately found to be the best threshold to use. So what this really means is that this many metabolites were harmonized across at least 6 studies, kind of a decreasing number of harmonized metabolites as we increase the study threshold. I think we had about 7 metabolites that we could actually measure in 45 studies. There was no metabolite that was measured in all 46 studies. If we look at the breakdown of the metabolites by pathway, so currently we're just assigning this based on metabolome superpathway. And you'll notice here the large portion of unknown. These are actually mainly from the Nightingale lab, who measure a slightly different kind of subset of metabolites and have a slightly different criteria to the other labs. So we're just working to assign them to a pathway right now. But excluding these unknown metabolites, the largest proportion were amino acids, were lipids, followed by amino acids, and then glycerophospholipids, which made up about 10% of the findings. So this is a volcano plot just showing the correlation coefficient and the minus log 10 p-value for every metabolite, each one of these 1,367 metabolites, again colored according to metabolome superpathway. And this was from a multivariable adjusted model with the adjustments that you can see here. So the first thing to note, if we use a very loose nominal p-value of 0.05, you can see that about 3/4 of the metabolites were significantly associated with BMI. Obviously, this is a very, that would be a very loose p-value to use, but even if we consider the kind of most stringent Bonferroni correction, still about 40% of our metabolites are significantly correlated with BMI. And I will say here that, you know, in general, we prefer not to use Bonferroni for metabolite data, just because of the existence of metabolites in these kind of highly correlated and co-regulated pathways. We really find Bonferroni to be a little too stringent. But if you know, even using this most stringent p-value, a very large number of metabolites were still significant. So we then applied this additional threshold of the strength of the correlation coefficient. I say strong here, we were actually using a cutoff of 1.15, greater than 1.15 or less than minus 1.15, which obviously really isn't particularly strong, but that was the threshold that we used to kind of tease apart these results a little bit more. And when we use this additional criteria, 224 metabolites were significant, 148 were positively associated with BMI, and 76 were inversely associated with BMI. And if we take a look at the top hits, so these are the top inverse associations based on both correlation coefficient and p-value. And you can see here, you know, for those who work with metabolomic data, at least in my experience, we very rarely see p-values anywhere near this close. So it was quite exciting to have such strong associations. And you can see among the top hits, the majority tended to be glycerophospholipids, which are involved in fatty acid and lipid metabolism, whereas the top hits that were positively associated with BMI, so increasing levels with increasing BMI, included a large number of amino acids, and particularly branch chain amino acids, which are a class that have previously, in a large number of studies, been associated with BMI before, due to their role in adipose tissue catabolism. So, you know, on both sides, kind of very biologically meaningful results. And this is obviously just a subset of those metabolites. These were just the top ones. We have the full list, but it really follows this same kind of pattern. You know, amino acids increasing, a large number of glycerophospholipids decreasing with increasing BMI. And as I mentioned, we do only have a small number of, relatively small number of cases, portion of people with prevalent diabetes at the time of blood draw. But obviously we're aware that diabetes is a very important metabolic disorder that has known impacts on the metabolome. So we just wanted to see how additional adjustment for diabetes status would affect the results. But you can see here remarkably strong concordance between the multivariable model and the multivariable model plus diabetes status. And this is just for the significant metabolites. So essentially, additional adjustment for diabetes really didn't have a strong impact on our results at all, which is one of the reasons why we kind of just focus on this multivariable model here. So those who are familiar with metabolomics will know that one of the things that we will normally do, kind of analogous to maybe gene set enrichment analysis, for those who work with genetic data, is look at pathway analysis for our significant metabolites. This is just a very simple figure here from Metaboanalysts. What this is doing for the 969 nominally significant metabolites, it's essentially performing a combined overrepresentation analysis. So for your set of metabolites, how many were in, were they enriched for a given pathway? But more importantly, it also takes this kind of pathway impact into account. So this uses pathway topology. So it looks at the metabolites that are driving the enrichment, and it determines whether or not they, kind of how important they are to the topology of that particular pathway. Are they a hub in the pathway, or are they just kind of a peripheral node? And it will score your pathway to have a higher impact if your metabolites are these hubs that kind of, if removed, your pathway would break down. So essentially, a higher pathway impact and a higher minus log 10 p-value indicates that your that pathway is particularly important among your set of results. So this was based on the 969 metabolites, and you can see a large number of amino acid pathways, the branched chain amino acids, were highly significant among our results. What the most of these top pathways that have in common is they're all involved in protein biosynthesis, which again is, obviously very important to BMI. So this is just a very simplified way of looking at these results as kind of a first pass. There are a number of issues with pathway analysis that I won't go into at this point, but this is just the beginning of our exploration of these pathways. There's a number of different approaches that we are taking to look a little bit deeper at the biology of our significant hits. The second aim of our study was to consider heterogeneity between the results. So were the associations consistent across all the different studies and strata of variables that we were looking at. So to do this, we use the Cochrane's Q value, which describes the percentage of variability in an effect estimate that is due to heterogeneity rather than chance. So the larger your Q value and the smaller the p-value associated with that Q value, the greater the chance that there is significant heterogeneity in your results. What you'll immediately see here that even among our very top, most significant hits, there did appear to be significant heterogeneity between the studies, which may lead us to question our results, or at least want to look at them in more detail. In fact, about 82 of our most highly significant metabolites were significantly heterogeneous. However, one of the problems with Cochrane's Q value is that it's very sensitive to large numbers. So if for example, we kind of dig in a bit deeper to this L-valine, which again is a branched chain amino acid that has been previously associated with BMI in a number of studies. So the Cochrane's Q would indicate significant heterogeneity. But if you look at this figure here, so this is just the correlation coefficient across all the different cohorts in which valine was measured. You can see that actually there was, although the effect estimates do differ slightly, they were kind of all consistent, and they were all in the same direction of effect within a relatively small, for the most part, narrow band, with only 3 of them not reaching statistical significance. And this can be attributed to a number of factors, including sample size. But really, when you look at this figure, you don't feel too concerned about the about significant heterogeneity. This figure here, again, is just the correlation coefficient and the minus log 10 p-value for valine across all the different strata that we looked at. And again, here it's a similar story. Although the significance level and effect estimate may differ slightly, they are all relatively coherent and consistent. And any differences are really driven by sample size rather than necessarily by biology. So for example, our Hispanic population was much, much smaller than the white population. We had a smaller number of known diabetes cases than cases, a small number of people under 20. So again, it seems that Cochrane's Q value might not be the best way to assess heterogeneity. And again, this is something that we are looking into further moving forward. But we were also interested, as well as between study heterogeneity, we were interested in between strata heterogeneity. So, you know, comparing males and females, comparing different regions. And what we found was that, when we consider the whole metabolome, there were some that did seem to have genuine biologically informative heterogeneity. And fasting status and gender seem to be the two biggest drivers of this heterogeneity. So if we look here, this is the p-value. This is a p-value from 0 to 0.9, and this is the number of metabolites with that p-value. So if there was no significant heterogeneity, we would expect a null distribution here. But rather what we see is a significant enrichment of significant p-values, indicating that there was some heterogeneity driven by gender. We see a similar thing for fasting status. And again, these are two variables that isn't perhaps not that surprising that we do see, biological heterogeneity. And these are things that we're now digging into a little deeper. In contrast, you can see that for something like case status, you really do get a null distribution, which was reassuring to us, given, I think one of the criticisms when you're looking at cohorts where a proportion of the participants go on to develop a given disease, you might be concerned that this is affecting your results, but it didn't really seem to be the case here for case status. So overall, what these results have told us is really, they tell us about a number of different pathways when you look at the results, or a number of different biological processes. Again, which it's not that surprising that our results would point to these processes that we kind of would assume based on the literature to be involved in a changing BMI, such as insulin resistance, altered glucose metabolism, oxidative stress. But I think more importantly, what these results really tell us is they provide this kind of proof of principle that it is feasible to perform large-scale meta-analyses across multiple diverse cohorts that include different populations, different profiling platforms, different labs. They include both targeted and untargeted data, and which include data generated both by NMR and by mass spec, and in serum and in plasma. And they really demonstrate that these meta-analyses can provide robust and biologically informative results with highly significant findings. And just on a level more related to BMI, we show that BMI is associated with increased levels of, in particular, branched chain amino acids and decreased levels of cholesterol, esters, and high density lipoproteins. So the next step, actually, this should change. We have now incorporated all studies, but we are, as I mentioned, looking further into this issue of heterogeneity. We're looking at the correlation between our top hits. Are we picking up all these branched chain amino acids purely because they're highly correlated with each other, and really, only one of them is of true biological interest? And we're also interested in developing metabolite profiles and signatures, related to the point above, in addition to individual metabolites. We're considering extremes of BMI, and we also have a subset of patients in whom we have adiposity measures. So we're also looking at the results in relation to those adiposity measures in that subset. And then finally, kind of more looking deeper into this idea of pathway and network interpretation and visualization. So the recruitment of studies for the BMI project is now finished, but COMETS is always recruiting, is interested in recruiting more studies. If anyone out there is working on a study that you think could benefit from being involved in COMETS, any participating investigator can submit a project proposal to perform their own meta-analyses. It just has to be approved by the steering committee, and then each individual cohort can decide whether or not they want to be involved in your meta-analysis. And really, there's a whole host of data out there just waiting to be explored. So if you are interested, please just get in contact. I'd be very happy to talk to you more about joining COMETS. And with that, I just want to thank the very large number of people who have been involved at all stages of COMETS Analytics and this particular project, in particular Jessica and Steve Moore and Steve's whole team. And thank you all for listening. I'd be really happy to answer any questions I have.